In this lecture, we will continue our discussion on the primal dual relationships. We look at three important theorems which are called the weak duality theorem, the optimality criterion theorem, and the main duality theorem. We will also look at a fourth thing called complementary slackness conditions. Let us look at each one of this in detail. The weak duality theorem is as follows. If the primal is a maximization problem, every feasible solution to the dual has an objective function value greater than or equal to that of every feasible solution to the primal. Now let us try to explain the weak duality theorem by considering the example. So maximize, we address the same problem, maximize 6x1 plus 5x2 x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. Now the dual will have two variables y1 and y2. So dual will be to minimize 5y1 plus 12y2 subject to y1 plus 3y2 greater than or equal to 6, y1 plus 2y2 greater than or equal to 5, y1 y2 greater than or equal to 0. Now let us consider a couple of feasible solutions for the primal. For example, zero 0 is feasible with z equal to 0. Let us consider a solution say 3 comma 3, 3 comma 1 let us say. So 3 comma 1 satisfies this, 3 comma 1 also satisfies this, so it is feasible to the primal. This would give us an objective function value of z equal to 6 into 3 18 plus 5 23 and so on. Now let us consider a couple of feasible solutions to the dual. For example, a solution 3 comma 3 would be feasible to the dual, 3 plus 9 is greater than 6, 3 plus 6 is greater than 5. This would have a value w equals 15 plus 36 is 51. If we consider another solution say 2 comma 1, 2 comma 1 is feasible, 3 into 2 6 plus 1 4 plus 1, so 2 comma 1 is feasible with w equal to 29 and so on. So we could evaluate any number of feasible solutions to the primal and to the dual, and we can easily compute and show that the primal being a maximization problem, every feasible solution to the minimization problem dual will have an objective function value greater than that of every feasible solution to the primal. Now the proof of the weak duality theorem is not very complicated. In fact, the way we have derived the dual, we have already assumed the weak duality theorem, because the way we derived the dual, we were only looking at whatever combinations that we saw when we were deriving the dual, they were all feasible solutions to the weak duality, to the dual, and they are all upper bound to the objective function value of the primal at the maximum. So the weak duality theorem follows from the way the dual has been derived. Let us go back and look at some more aspects of the weak duality theorem. Now we have written the primal and dual to the problem, and there exists a feasible solution x1 x2 to the primal, assuming that there exists a feasible solution. Now we have x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12. So every feasible solution to the primal should satisfy these two. Now if there is a feasible solution to the dual, Now substituting the objective function value of the solution feasible to the dual we will get. Now W will be greater than or equal to, now if I have a feasible solution to the dual, then we would have that feasible solution to the dual will be 5y1 plus 12y2, and if we have a feasible solution to the primal x1 x2, then x1 plus x2 is less than or equal to 5. So this solution that is feasible to the dual, which is equal to 5y1 plus 12y2, will be greater than or equal to, because 5 is greater than or equal to x1 plus x2, now this will be greater than or equal to x1 plus x2 into y1 plus 3x1 plus 2x2 into y2. Now that is shown here. So this feasible solution to the dual W will be greater than or equal to x1 plus x2 into y1 plus 3x1 plus 2x2 into y2. Now when we simplify this, we have x1 plus x2 less than or equal to 5 and 12, substituting we get this. Now rearranging the terms, you would have now W is greater than or equal to x1 into y1 plus 3y2. Look at this expression and look at the next expression. We are now arranging them in terms of x1 and x2, we are grouping them in terms of the terms for x1 and x2, we get y1 plus 3y2 plus y1 plus 2y2. Now since y1 y2 are feasible to the dual, we realize that y1 plus 3y2 is greater than or equal to 6, y1 plus 2y2 is greater than or equal to 5, substituting W will be greater than or equal to 6x1 plus 5x2. And since x1 and x2 are feasible to the primal, z is 6x1 plus 5x2, so W is greater than or equal to z. So weak duality theorem is almost a very obvious result the way we have derived the dual. So if the primal and dual have feasible solutions, or for every feasible solution to the primal and every feasible solution to the dual, every feasible solution to the dual will have an objective function value higher than that of every feasible solution to the primal. We can look at it in a different way. If the dual is a minimization problem, every feasible solution to the dual will have an objective function greater than that of the optimum. Primal being a maximization problem, every feasible solution to the primal will be less than or equal to the optimum of the primal. The way we have derived the weak duality theorem, every feasible solution to the dual is an upper bound to the optimum value to the objective function value at the optimum of the primal, and hence weak duality theorem follows. Weak duality theorem is a very important result. We assume the primal to be maximization, dual minimization. Every feasible solution to the dual will have an objective function value greater than or equal to that of every feasible solution to the primal. Now let us go back to the second theorem, which is called the optimality criterion theorem, and this is as follows. If primal and dual, we represent them as P and D, have feasible solutions such that W equal to Z, then these are optimal to primal and dual respectively. For example, if we go back here and say that the primal has a feasible solution, say two comma 3 with 6x1, the objective function was maximize 6x1 plus 5x2. So if we have a feasible solution 2 comma 3 with z equal to 27, now dual has a feasible solution. Dual was minimize 5y1 plus 12y2. So we say dual has a feasible solution with 3 comma 1 with w equal to 27. Remember, primal now has a feasible solution 2 comma 3, 6x1 plus 5x2 is 27. Dual has a feasible solution 3 comma 1. Now let us go back to the problem. The primal constraints are x1 plus x2 less than or equal to 5 and 3x1 plus 2x2 less than or equal to 12. Now 2 comma 3 satisfies, 2 plus 3 equal to 5, 6 plus 6 equals 12 and has an objective function value of 27. The dual constraints are y1 plus 3y2 greater than or equal to 6 and y1 plus 2y2 greater than or equal to 5. Now let us look at 3 comma 1, 3 plus 3 into 1 is 6, 3 plus 2 5. So 3 comma 1 is feasible to the dual, has objective function value 27, 2 comma 3 is feasible to the primal, has objective function value 27. Based on this theorem we can go back and say that this is optimal to the primal, this is optimal to the dual. If you look at it very carefully, the optimality criterion theorem is only an extension of the weak duality theorem. If for example these two are not optimal to primal and dual respectively, then this should have a feasible solution with greater than 27. Then it will straight away violate the weak duality theorem, because weak duality theorem says every feasible solution to the dual will have an objective function value greater than or equal to that of the primal. By the same logic we can prove that this is optimal to the dual. So the optimality criterion theorem says that if primal and dual have feasible solutions with the same value of the objective function, then those solutions are optimal to the primal and dual respectively. Now the third one is called the main duality theorem, which is this: if primal and dual have feasible solutions, then both have optimal solutions with z star equal to w star with the same value of the objective function. This is a more general statement because it assumes that if P and D have feasible solutions. Now the first part of it can be looked at more from the fundamental theorem of linear programming. That is the reason we saw the fundamental theorem. Now every linear programming is either feasible or has an optimum or unbounded or infeasible. So there are three things. Now it has an optimum, can be unbounded and infeasible. Now if we assume that P and D have feasible solutions, it means that neither of them is, or we have to make sure that neither of them is infeasible, because if either the primal or the dual are infeasible, then they will not have feasible solutions. Therefore this is taken care of. Now it simply means primal and dual have an optimum or unbounded. Now if one of them is unbounded, then the weak duality theorem will give us some results. It will make sure that somewhere it will be violating some of the weak duality conditions, because one of them will be having an infinity. So the weak duality theorem will be violated. Therefore we look at the situation where both will have feasible solutions, then both should have optimum solution. Then for example if both have feasible solutions, both cannot be unbounded or infeasible. So both will have optimal solutions. And the moment we agree that if both will have optimal solutions, then automatically the optimality criterion theorem takes over and says that the optimum values will have to be equal. Otherwise the weak duality theorem will be violated. In any case we are not going very deep into these theorems, but we just state them so that we understand that these theorems exist, and these theorems define the relationships between the primal and the dual. We now move into another one called complementary slackness conditions, which is this: if x star and y star are optimal solutions to primal and dual. In fact we would define something more here. We have x v plus y u equal to 0. This is called complementary slackness condition. We have to define what these v and u are. x and y are the solution vectors corresponding to primal and dual respectively. U and v are also vectors which are slack variables corresponding to primal, corresponding to dual respectively. So, if the primal has x is the vector of decision variables for the primal, u is the vector of slack variables for the primal, y is the vector of decision variables for the dual, and v is the vector of slack variables for the dual, then at the optimum x into v plus y into u equal to 0, x, v, y, u are all vectors because and dot product. Therefore, this can be generalized as sigma x xi vi plus sigma yj uj equal to 0 because it is a dot product. And since in the given problem x, y, u, v are all greater than or equal to 0, then for every individual xi corresponding xi vi equal to 0 for all I and yj uj equal to 0 for all j. I and j are used because the primal may have different number of constraints and different number of variables. X is the number of decision variables in the primal. This is the number of decision variables in the primal. So, this many constraints the dual will have, this many slack variables the dual will have. So, xi yi, xi vi is taken care of. Similarly, y is the number of decision variables in the dual, which is the number of constraints in the primal, and each constraint in the primal will have a slack. So, j essentially represents the number of variables in the dual, which is the number of constraints in the primal, and I represents the number of variables in the primal and the number of constraints in the dual. So, because x, y, u, v are all greater than or equal to 0 in the linear programming problem, for every I xi vi equal to 0, yj uj equal to 0. So, what does it tell us? It tells us that at the optimum, if a particular variable x is a basic variable and takes a positive or a non-negative value, now let us leave out things like degeneracy and alternate optima for a moment. If a particular x is a basic variable at the optimum, then the corresponding dual slack will be equal to 0. If a particular dual variable is basic at the optimum, then the corresponding primal slack will be equal to 0. If a particular dual slack is 0 or if a particular dual slack variable is non-basic at the optimum, then the corresponding, or if this is basic at the optimum and takes a value, then the corresponding primal decision variable will be non-basic, and so on. So, this is what the complementary slackness tells. Now, let us go back to the complementary slackness condition and try to learn a few more things about it, considering the same example that we have. Now, the same example that we have, we maximize 6x1 plus 5x2. So, let us write the same example here. Maximize 6x1 plus 5x2 subject to x1 plus x2 plus u1 equal to 5. Remember, the slack x3 has now become u1 and 3x1 plus 2x2 plus u2 equal to 12, slack x4 has become u2, x1, x2, u1, u2 greater than or equal to 0. Now, dual is minimize 5y1 plus 12y2, y1 plus 3y2 minus v1 equal to 6, y1 plus 2y2 minus v2 equal to 5, y1, y2, v1, v2 greater than or equal to 0. First, let us look at the solutions and then verify the complementary slackness, and then let us go back and do something more with the complementary slackness. So, primal has a solution which is x1 equal to 2, x2 equal to 3, z equal to 27, x1 equal to 2, x2 equal to 3 makes u1 equal to 0, u2 equal to 0, z equal to 27. Now let us assume we know the optimal solution to the dual. So optimal solution to the dual is y1 equal to 3, y2 equal to 1, z equal to 27. Primal and dual will have the same value of the objective function at the optimum. Now y1 equal to 3, y2 equal to 1 would make v1 equal to 0, y1 equal to 3, y2 equal to 1 would make v2 also equal to 0. Now let us go back and apply the complementary slackness conditions. Xv equal to 0, yu equal to 0, x1 v1 is 0 product, x2 v2 is 0, y1 u1 is 0, y2 u2 is 0. So complementary slackness is now satisfied at the optimum. Now let us do something else. Let us go back and see that the same thing is shown here on the PowerPoint slide. The fact that you written the primal and the dual, and we can verify the complementary slackness from that. So next slide. Now let us go back and apply the complementary slackness to the next problem, the same problem that we had worked out earlier, which is the problem maximizing 3x1 plus 4x2 subject to all these. Now the dual is also written here, 12y1 plus 30y2 plus 36y3. This problem we have solved earlier in one of the early lectures. Now for this problem, the optimal solution to the primal is x1 star equal to 6, x2 star equal to 6, u3 star equal to 6. If you remember, x5 was 6, x5 is u3, z equal to 42. The dual solution would be y1 star equal to 1, y2 star equal to 1, w equal to 42. Now if you look at it very carefully, if you apply the complementary slackness to this, you realize the x1, now let us go back to that solution, x1 equal to 6, x2 equal to 6, u3 equal to 6, u1 equal to 0, u2 equal to 0. This is the optimal solution to the primal. Optimal solution to the dual is y1 equal to 1, y1 equal to 1, y2 equal to 1, and the rest of them are 0. So you will have y3 equal to 0, we have v1 equal to 0, v2 equal to 0. The primal had 3 constraints, so we have 3 basic variables. The primal has 2 variables, so dual will have 2 constraints and it has 2 basic variables. Complementary slackness is straight away satisfied. What is also important is this: there is a primal slack in the basis, corresponding dual decision variable is non-basic. There is a primal decision variable in the basis, there is a corresponding dual slack is non-basic with 0. This is the most important thing. There is a primal slack variable in the basis, so the corresponding dual decision variable is non-basic with 0 from the complementary slackness conditions. Next, we are explaining the same thing here, slack, the next one. Now the next thing we can do is this. Now for this example, what we have tried to do is, we have written the complementary slackness conditions and we have verified the complementary slackness condition. Now let us do something. Let us assume that we do not know the optimal solution to the dual. Let us assume that we know the optimal solution to the primal. The only thing that we know is the optimal solution to the dual will have w equal to 27. Let us assume we do not know which are the basic variables at the optimum and what values they take. Now we can find that out using the complementary slackness. Now this is the optimal solution to the primal. So x1 is basic, so v1 is non-basic and equal to 0. x2 is basic, v2 is non-basic and equal to 0. u1 equal to 0, u2 equal to 0 implies y1 and y2 are basic. So all we need to do is go back and substitute here, substitute v1 equal to 0, v2 equal to 0. If we solve y1 plus 3 y2 equal to 6, y1 plus 2 y2 equal to 5, the values that y1 and y2 will take are optimal, and they turn out to be 3, 1 with the value 27. Similarly, you can go back to this example and then using the complementary slackness conditions and the optimal solution to the primal, you can go back and compute the optimal solution to the dual. Now the moment we solve the primal, what we do is we know the solution to the primal, the optimal solution to the primal. We also know the value of the objective function at the optimum. Now we do not have to solve the dual from the beginning. All we know the moment we solve the primal, and if the primal has an optimum, assuming a finite unique optimum, then the dual also has an optimum with the same value of the objective function. But we do not know what the solution of the dual is. Now in order to get the solution of the dual, you need not solve the dual all over again separately as a linear programming problem. By looking at the solution to the primal, one can apply the complementary slackness conditions and straight away get the solution to the dual. So that is something which is now possible. Now let us go back to this. So we can evaluate the optimum solution to the dual if the optimal solution to the primal is known and vice versa, etc. We look at all those conditions. From the optimum solution, x1 star equal to 6, x2 star equal to 6, u3 equal to 6. So in this example we would know that it is enough to solve only for y1 and y2. This problem, there are 2 variables and 3 constraints in the primal, 2 variables and 3 constraints, 3 variables and 2 constraints. So we have 2 constraints in the dual, we just need to solve only for y1 and y2, rest of them will be 0. So y1 y2 is the optimal basis for the dual, and we can solve it to get the solution to the next problem as well. Solve for y1 plus 2 y2 equal to 3, y1 plus 3 y2 equal to 4, which would give us y1 star equal to 1, y2 star equal to 1 from here, and z equal to 42. So using this solution, if we know this solution, you can once again apply the complementary slackness condition and go back to the other one also. That is also possible. Now let us look at another aspect. Now what is this dual, and let us try to give a mathematical explanation to the dual. We have already seen some aspects of primal and dual relationships. We will try to see a few more, and we will also try to understand where and how we see all those in the simplex table, which so far we have not looked at. Now let us look at this called mathematical explanation to the dual. We take the same example and do this. Now right now we will note down the solution to the dual here. This is the dual. Solution to the dual is y1 equal to 3, y2 equal to 1, and z equal to 27. Now let us look at this problem, primal again, and let us write this as less than or equal to 5, less than or equal to 12, and right now let us leave this. Now let us assume that we know the solution to this problem and so on. Let us assume that this right hand side increases by a small quantity delta. We make this delta very small, and we assume that when this becomes 5 plus delta, remember that x1, x2 are the basic variables here at the optimum, which we know. We know without this delta, we know the solution x1 equal to 2, x2 equal to 3, z equal to 27. So we assume right now that with the inclusion of this delta, x1 and x2 would still continue to remain optimal. So let us try to solve this for x1 plus x2 equal to 5 plus delta and 3x1 plus 2x2 equal to 12. Assuming that x1, x2 will be the basic variables at the optimum. Now multiply this by 2 to get 2x1 plus 2x2 equal to 10 plus 2 delta. So this would give us x1 equal to 2 minus 2 delta. Substituting, x2 is equal to 5 plus delta minus x1, this is 5 plus delta minus 2 plus 2 delta, which is 3 plus 3 delta, and z is 6x1 plus 5x2 equals 6 into 2 minus 2 delta plus 5 into 3 plus 3 delta, which is 27, minus 12 delta plus 15 delta plus 3 delta. So what happens is, if we increase this right hand side resource by a very small value delta, then the decision variables change. This is assuming that x1, x2 would continue to be the basic variables. x1 becomes 2 minus 2 delta, x2 becomes 3 plus 3 delta, and z becomes 27 plus 3 delta. Now what is this 3 delta? Now is this 3 the same as this 3? For example, if we make this 5 minus delta, would we get 27 minus 3 delta here? If this 3 is the same as this 3, then if we had retained this as 5 and if we had made this as 12 plus delta, then would this have become 27 plus 1 delta? The answer to all these questions is yes, provided x1 and x2 continue to be the basic variables at the optimum. So what we try to explain here is, the dual variables value is actually the rate of increase of the objective function of the primal for a small increase in one of these resources. If the first resource is increased by a small quantity delta, the objective function will now increase by a quantity 3 delta, where this 3 is the value of the corresponding dual variable. If the second resource is increased or reduced by a small quantity delta, then we can go back and easily show that the objective function will increase or reduce correspondingly by this. So what does it mean? It means the dual can now be explained as the marginal value of the resource, or the dual simply represents the extent. Mathematically, the value of the dual variable represents the extent to which the objective function will increase or decrease for an incremental increase or decrease of the corresponding resource, and that is the explanation, mathematical explanation to the dual variable. Now one can continue with this exercise by putting a minus delta and can show that it will become 27 minus 3 delta and so on. So let us go back to this. Now the increase in objective function value at the optimum, the most important thing is the term at the optimum. The dual has a meaning at the optimum. It actually does not have a meaning at other places other than the optimum. It also has a good physical interpretation which we will see later, but right now we are considering all these at the optimum. And how are we ensuring this at the optimum in this calculation? We are ensuring it by assuming that x1 and x2 will be the basic variables. So the optimum basis will remain intact. So at the optimum, for a small increase of delta of the first constraint, the actual value in the objective function is 3 delta, where 3 is the value of the first dual variable at the optimum. Now the value of the dual variable at the optimum is the rate of change of the objective function for a small change in the value of the resource. It can be viewed as a change in objective function for a unit change at the optimum, assuming that the change is not significant enough to replace the basic combination. As long as the same basic variables are intact, the dual can be interpreted as the rate of change of the objective function with respect to the resource. Yeah. Now let us go back to the economic interpretation of the dual. Now let us do this. Now let us assume that this is the primal that we are looking at and this is the dual. Now let us go back to the problem formulation. Let us assume that these 5 and 12 are two resources which we call R1 and R2, and x1 and x2 are the amount of product that is made. Now what does this tell us? It tells us that if instead of 5 quantity of the resource that I have here, if I had a 5 plus delta, then it is possible for me to make a 3 delta more than this. Or interpreting it physically, if I have one more resource with me, if the 5 had become 6, then that resource is capable of giving me 3 more rupees in terms of the objective function. Or to me, the value of the additional resource from 5 to 6 is rupees 3. Or if I have to go and buy this additional resource from the market, then I will be willing to pay a price which is 3 rupees or less for this resource. If someone is willing to sell me the 6th unit of this resource for 3 rupees or less, then I know that by buying this resource for 3 rupees or less, I will make 3 rupees more to my objective function and I will happily buy it. So it is a marginal value at the optimum of this resource, or the price that I am willing to pay to get an additional unit of this resource. Now that is the interpretation of this dual variable. Similarly, the next dual variable y2 will be the additional price that I am willing to pay for one more unit of this resource, which is 1 rupee. Now why then do we have the same value at the optimum for the primal and dual? Let us look at this. Let us assume that primal is the carpenter or the producer who makes these two products, and let us right now assume that the person does not have any of these resources but has planned for 5 and 12 respectively, and let us also assume that he will go to the market or to a common place to buy these two resources 5 and 12. Now let us assume that there is some other entity or an individual who is selling exactly these two resources to this person. Now the person who is selling the resources is actually solving the dual, that is his problem. So the person, let us assume, has already solved the dual knowing the requirements of this man, and now will price these resources at 3 and 1 respectively. So this person will be looking at getting the first resource for 3 rupees or less, and this person knows that the value of the first resource is exactly 3, and this person will not sell it for less than 3, because if this person is selling it for less than 3, this man will happily buy and make more money. This person would like to sell it for 3 or more, knowing fully well that the marginal value is 3, and if this person is selling it for more than 3, then this one will not buy because he would make a loss by buying it for more than 3. So both will agree that this value of the resource is exactly 3. Therefore at the optimum 5, 12, both of them know that the value of the resource is 27, which is the optimal value of the objective function of the dual. At the same time, the person will also make 27 rupees. So this is called the economic interpretation of the dual. The worth of the resource is equal to the money that this person makes. So physically, every dual variable can be interpreted as the marginal value or the price that the person is willing to pay at the optimum to procure one additional unit of the resource or any small value delta of that resource. Right. From the previous discussion, we know that the objective function increases by 3. If we have to buy the resource, we will be willing to pay a maximum of 3 rupees for the unit increase. Otherwise, we will end up making a loss and will not be profitable considering the purchase of the extra resource. So the value of the dual variable is the marginal value of the corresponding resource at the optimum. So now we go back and interpret it. Now the same explanation that I gave here is now seen in the PowerPoint slide. So both the carpenter and the seller, carpenter is the primal, the producer, the seller is the resource or the market, will agree that rupees 3 in a competitive environment, and each will be making their money and the associated profit. Now if you look at the next problem, we get another interesting interpretation of the dual that we should be seeing here. Now let us go back to this problem. Now this problem now has, the problem is maximize (3x1 plus 4x2) subject to x1 plus x2 less than or equal to 12, 2x1 plus 3x2 less than or equal to 30, x1 plus 4x2 less than or equal to 36. If you look at the optimum solution to this, you find what are the 3 dual variables, y1, y2, y3 are the dual decision variables. From the optimal solution to the dual, we realize this is y1 equal to 1, this is y2 equal to 1, y3 equal to 0. It means that if I make this 12 as 13, if I make this increase it by delta, let us say, the objective function will become 42 plus delta. Now this is z equal to 42, this is w equal to 42, which means I am willing to pay 1 rupee more for this resource, I am willing to pay 1 rupee more for this resource, I am willing to pay only 0 for this resource. Why? The reason is, let us go back to the solution. x1 equal to 6, x2 equal to 6 means I have 36 units of this resource, the requirement is 6 plus 24, 30. I have not utilized this resource fully, I already have 6 resources with me. So right now it does not have any marginal utility. I do not have to go to the market and pay for an extra resource, it does not cost me anything. So the marginal value of a resource that is not completely utilized is 0 because the resource is already available. Now that is shown by if a slack variable is present in the basis, which means the resource is not fully utilized, then the corresponding decision variable will take a value 0. So this is also an explanation that we should understand. So sometimes the dual decision variable can take value 0, indicating that in the primal some resource is available and not entirely utilized. That is shown as a slack variable in the basis of the primal. Now that I think is shown here. So when the slack variable is in the basis, corresponding dual decision variable is non-basic, indicating that the marginal value of the corresponding resource is 0. Yeah, next. Now let us look at something else. Let us look at the simplex method. What does the simplex method do? So far we have solved the given problem, the primal, using the simplex method. Now does the simplex method give us any clue about the dual, or does it explicitly look at the dual and try to solve the dual? So that is something which we need to look at now. Now let us do that. Let us go back to the same example and look at the simplex table for this example. Yeah, the next slide. If we go back to this, we are only showing the optimal, the last iteration of the simplex table. I am not showing all the intermediate iterations now. We are only looking at the final simplex table for this problem, and the final table would be 6, 5, 0, 0. We have x2 and x1. This is the optimum table in the simplex. We get 0, 1, minus 1, 0, 1, 3, minus 1, 3, 1, 0, minus 2, 1, 2, Cj minus Zj, this is 5 and 6, 0, 0, 5 into 3, 15, 6 into 2, 12, I get a minus 3, 5 into minus 1 is minus 5, 6 into 1 is 6, I get a minus 1, I get Z equal to 27. Now the question is this 3 with a minus sign, and is this 1 with a minus sign? The answer again is yes. Now simplex has a way to show the optimum solution to the dual also. Simplex not only solves the primal, but simplex also solves the dual. Now whatever we see here as Cj minus Zj, at the optimum, because we are solving a maximization problem and we are using Cj minus Zj, our termination condition is the non-basic variables should have a negative value at the optimum. Now at the optimum, for a maximization problem, if you take the Cj minus Zj and multiply it with a minus 1, then you realize that you will have the values of the dual seen somewhere else, and it is always seen here. We will show that also in the next couple of minutes. Now x1 and x2 are the primal decision variables. So what we do here is we write this as u1 and u2, which are the primal slack variables. Now x1 and x2 are primal decision variables. From the complementary slackness, their corresponding dual slacks are v1 and v2. These are the primal slack, so they correspond to y1 and y2. Now what we see here as Cj minus Zj is nothing but the solution to the dual for the dual decision variables as well as the dual slack variables. Now here you can go back and see y1 equal to 3, y2 equal to 1, but with a minus sign, of course, that is because of Cj minus Zj. You need to multiply this with a minus 1. So you get y1 equal to 3, y2 equal to 1, now v1 equal to 0, v2 equal to 0. This is the solution to the dual. Solution to the primal, x1 equal to 2, x2 equal to 3, u1, u2 which are not there are equal to 0. So at the optimum, the simplex algorithm not only solves the primal but also is capable of showing the solution to the dual. In any case, we know that the value of the objective function is the same 27. So the solution of the dual is seen as the Cj minus Zj values with a negative sign under the corresponding slacks. Now these are the primal slacks, they correspond to the dual decision variable. Primal decision variables correspond to the dual slack. So this Cj minus Zj row can now be seen as a dual solution row, and the right hand side is seen as a primal solution column. The right hand side will show only the basic variables of the primal with the corresponding values. The rest of the variables are non-basic at 0, and the Cj minus Zj row at the optimum multiplied with a minus sign, because at the optimum this row is entirely non-negative. So we multiply this with a minus 1, we will get the corresponding solution to the dual, solution of both the basic decision variables as well as the slack variables. So simplex is capable of showing the solution both to the primal as well as to the dual in this example. Now why simplex is doing it, is capable of showing, or why is this the optimum solution to the dual, we will see a little later in this course when we look at matrix methods for solving linear programming problems. We will show how exactly this method becomes, or these values become, the optimal solution to the dual. The simplex also does a few interesting things. If the Cj minus Zj in the optimum iteration is capable of showing us the solution to the dual, then is there an interpretation for the Cj minus Zj's in an intermediate iteration? If you take this problem again, if you take the same problem that we solved, we took 3 iterations to solve this. We had the first iteration which was initialization, then we had an intermediate iteration, and then we had this as a final iteration. Now the Cj minus Zj in the final iteration, if it can show us the dual solution, what is the explanation for the Cj minus Zj in the intermediate iterations? So that part of it, as well as the complementary slackness conditions, we will see in the next lecture.